Gather around, boys and girls. We're going to have some story time. This is the story of Matharella. Matharella was a beautiful princess who had 3 ugly stepsisters. And they were jealous of Matharella because she was so pure and logical. And they weren't. Matharella didn't mind, though. She was just happy to be dreaming about the big Pokemon Go raid that the prince was planning at the castle. But on the night of the raid, her stepsisters made her stay home to teach scientific notation. But I don't use scientific notation, she said. You should teach it. They just laugh. Sucks to be you. Which is why we are going to be looking at 5.2 scientific notation. By the way, that was a totally true story. Here we go. Math 60, 5.2 scientific notation. Let's hit it. First, we're going to do some review. So, because we just finished a section all about exponents, we are going to go ahead and review some powers of 10. So, at first, if I just gave this to you, there'd be no way to know where I'm going with this. So, 10, I'm going to write as 10 to the first power. 100 is then, we can do this Dora style, 100 is 10 to the what? You're right. It's 10 squared. 1,000, yep, is 10 cubed. Now, when we go to decimals, sometimes it's hard to remember. So I'll remind you that this guy is 1/10. So it's written as 1 over 10 or 10 to the negative 1, right? We just studied these in the last section. This is a negative exponent. The second one down is 1/100th, which I don't think anyone can say without spitting, which is 10 to the negative 2. Remember, it's 100 in the denominator, so that's 10 squared in the denominator. It's actually a vampire, 10 to the negative 2. And then this last one, even though I don't have enough room, because these vampires are very large, is 1/1000th, which is really hard to say. And that's going to be 10 to the negative 3rd power. So something to notice is for numbers greater or powers of 10 greater, 10 and greater, if you look at the exponent, it tells you how many zeros there are. So 1 0 is 10 to the first, 2 zeros is 10 squared, 3 zeros is 10 cubed. For numbers that lie to the right of the decimal point, you look at their spaces. So this is 1 decimal place to the right of the decimal point, so it's -1. 2 spaces to the right, -2. 3 spaces to the right, -3. So that's another way to remember it. So what the heck is scientific notation? Well, basically, scientific notation is a coping mechanism of the other sciences who are not pure and not logical the way Matharella is. And they have to deal with really big or really small numbers often. And so it's a way to quantify numbers so that you can very easily compare them to each other and very easily see how big they are. For example, and I'm skipping over what I wrote there, so I'll come back to it in just a second. I'm going to look at these 2 numbers. For example, I wrote a number that's really big. 1, then it's 2, 4, 3, and then it's got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 zeros. So this would be hundreds, thousands, millions, billions, trillions, quadrillions. So this is 1,243 trillion, and whatever we're counting, dollars or grains of sand or whatever large thing the physicist has to look at. And in a similar way, this number is a very small number, right? If we look at tenths, hundredths, thousands, 10,000s, 100,000s, millionths, 10 millions, 100 millions, 1,000 millionths, etc. This is a tiny, tiny number. One of the downsides of both of these numbers is they're very hard to express to people. If I were going to try to tell you how to write this down, I would have to tell you how many zeros there are. I couldn't just sit there and go 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. It'd be very hard to keep up. In the same way, this is going to be hard to deal with. So if I want to compare these, if I want to share them, like you're always sharing numbers, at parties and stuff, math parties, we're going to come up with some very interesting ways of kind of bringing them down to a style of writing and a way of writing them so that we can really see what's involved. So back up here. The way we're going to approach scientific notation is pretty much the vanilla style. Every different science, every different field that uses scientific notation could possibly make some flourishes, make it a little fancy, have some chocolate syrup. There are a lot of different ways to approach this. So from a mathematical perspective, we teach one method, and then that'll be the plain style. And then when you go into your field, they may say yes, and we're going to add some toppings. So I'm going to always write my numbers with one digit to the left of a decimal point. At which point you're going to say, wait. What about all those numbers? I'm going to say, yes, I understand, but follow me here. One number to the left, a decimal point, and then whatever other numbers I have to until I run out of non-zero numbers. I don't have to write in all the zeros at the end, just numbers until we're done with the non-zeros. And then a big old X so that everyone knows that this is not the letter X, like a variable. And then 10 with an exponent. And the exponent can be positive or negative. And basically the 10 to that power is going to tell us, do we have, oops, I'm pointing to something you can't see. Do we have something large or do we have something small? So let's go through, before we get to those big numbers, let's go through a couple of examples to show you what the heck I'm talking about. So the number 35. Oops, I got ahead of myself. Ignore that little dot. Okay, so the number 35, if you do not see a decimal point, the decimal point is assumed to be at the end of the number. This is a whole number, 35, so it would be 35.0. I want to move the decimal point until there's only one digit to the left of the decimal point. So I'm going to move it this way. And I'm going to count how many spaces I moved it. I moved it one space. Now I'm going to write this as 3.5. I know these two are not equal. Right now, there's no way these are equal. This is 35. This is 3.5. These are totally different numbers. However, then what I'm going to do is I'm going to say, well, basically it was 3.5 times, and then I'm going to say, okay, well, in order to get this into this really interesting stylized form, I had to move the decimal point one spot. So I'm going to say I moved the decimal point one spot. This is actually 3.5 times 10, which if you think about it, 3.5 times 10 would be 35. And so this tells me that 35 has a magnitude that matches other numbers that basically are, say, 3 or 4 or 5 times 10. So I'm able to see really easily and quickly how big it is and compare it to other numbers, which is kind of nice. Now, what if I had 0.35? Well, to a certain extent, it's easier because you've got the decimal point right there. In this case, I'm going to be moving the decimal point one space to the right because, again, I want this to have one digit, non-zero digit to the left of the decimal point, then a decimal point, and then whatever else I got. Now, this number had started out small. I moved it one space, so I'm going to write it as 10 to the negative 1. Now, here's the thing. I'm supposed to teach this to you by teaching you left means one thing and right means another, and that is completely beyond me. Folks with dyslexia, well, me with dyslexia specifically, I don't really know my left and my right very easily, and remembering rules like that are very difficult for me. So the way I do scientific notation, kind of rogue scientific notation, Princess Mathrella. Oh, oh, sorry. I got a frog in my throat. I'm still getting over that cold. Sorry. The way I'm going to do it is if it's a large number, it's 10 to a positive exponent. So by large, I mean larger than 1. If it's a small number, smaller than 1, it's going to have a negative exponent. That's it. No remembering left and right. If you want to look up the left and right rules, go for it. A lot of people love them. I hate them. They can just live with the stepsisters. Okay, shall we do the complicated ones? Woohoo! Love a challenge. So first thing is to realize that if this is a whole number, then the decimal point is right there. Sometimes you'll have decimal points in the middle. This one doesn't have one written in, so it's at the end. And then we're going to move this, and I'm going to count how many spaces. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And I'm going to stop right there. 5, 6, 7, 9, 10, 11, 12. I'm running out of room. 13, 14, 15. So I had to move it 15 spaces. Now, here's the thing. I'm going to write 1.243, and then I'm going to stop because that's the end of the non-zero numbers. This was a very large number, so it's going to be 10 to a positive exponent. And what's the exponent going to be? You're right. It's 15. Woohoo. You guys are brilliant. I'm going to do the same thing over here. Remember, with the decimals, the ones that are always already written with decimal points in them, it's a lot easier to do because the decimal point is already there. So let's go 1, 2, 3, 4, 5, 6. I'm just going around every 0. 7, 8, 9, 10. I think it was 10. Let me count again. 4, 5, 6, 7, 8, 9, 10. Poor Mathrella, stuck doing scientific notation instead of going to the big Pokemon Go raid. Boy, those mean stepsisters are pretty mean. You should probably write a letter to someone saying, hey, we should get the stepsister sciences to teach their own scientific notation. Right? That would be a good use of your time. Okay, so I moved the decimal point 10 spaces. And again, notice that I made sure I moved it right between the 4 and the 6. There's always a single number, a decimal point, and then whatever other numbers you've got. We always do that times 10 to something up here, positive or negative. I made this a negative 10 because it's a small number. So far, so good? Woohoo. Shall we try the second page? I know this is getting exciting, isn't it? Almost worth missing the big raid party, but not. Convert to standard notation. So once we've got numbers in scientific notation, we can figure out what standard notation number they refer to. But let me just take a moment to point out, I've written these 3. They all have the same first number. I'm sure people who are actually, authentically math teachers know what this is called. It's probably the abscissa for all I know. The first number here is the same for all 3. But notice that it's the exponent that tells you this is a large number, this is a pretty small number, this is a honkin' large number. So we can very easily compare. And in fact, if I wanted to really push it, I could say, well, what's the difference between these two? Well, the difference in magnitude isn't just positive 5 and negative 5. It's all the way from negative 5 to positive 5. So this is 10 to the 10 difference, if that makes sense. And from negative 5 to 13, that's 10 to the 18 difference. I don't even know off the top of my head what that would be called. So, okay, how do we do this? 1.036. And we look at this and we say 10 to the 5th means it's a large number. So I'm going to make it a large number. 1, 2, 3, 4, 5. I count off 5 spaces. If there are any spaces that don't have numbers, I'll just put zeros in them. So I've got 1,036,00, and I could put my comma in 103,600. Now, oops, you guys can't see it. Ta-da! There we go. Secret number over here. If you've ever talked about a 5-figure or a six-figure salary, this is a very similar way of looking at it. Notice that's a little bit different. 10 to the 5th, because there's already a digit on the left side, actually leads us to a 6-digit number. So it's a little bit different, but similar. Okay, for this one, we know it's going to be a small number. So I'm actually going to start over here because I'm going to have to go smaller. So I have to go to the left. 2, 3, 4, 5. 2, 3, 4, 5. So let's see. I think I've got. I'm going to write in my leading 0. I don't think it's a misleading 0. I think it's just a leading 0. 2, 3, 4, 1, 0, 3, 6. So there we go. 4 zeros and then 1 0 3 6. And hopefully, if you look at this and you look at this, you can see the appeal of writing the number this way, just because it's more compact. It squeezes out all the excess zeros, so you don't have to carry them around. It's like a number but concentrated. Okay, now for this one, I need a lot of space. Because this is going to be times 10 to the 13th, which is a positive exponent, so it means it's a large number. 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12, 13. So let's see how many zeros there are. 7, 8, 9, 10. 10 zeros. 1, 0, 3, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh my goodness, counting backwards. There's a comma, there's a comma, there's a comma, there's a comma. Thousands, millions, billions, trillions, 10 trillion, whatever we're counting. So far, so good? Awesome. Let's do a couple of other problems. Now, I have set up this problem so it works really nicely, but the point of this first problem is to show you the power of using scientific notation in calculations. So instead of writing this out as 42 with 5 zeros, and this one is 21, written as a small number. And notice that the way that these have been written, I took these out of the book. These are not actually in proper scientific notation. They're kind of in a modified scientific notation. But if we have these two, notice that, and again, the X is written in a big X like that, so no one mistakes it for a variable. It's a big old times. Notice that if I've got the magnitude split off from the number there, I notice that 42 is divisible by 21. Wow. And then I think to myself, wait a minute, this is 2 over 1. 10 to the 5th over 10 to the negative 3rd, that's 2 times 10 to the 5 minus a negative 3rd, or 2 times 10 to the 8th. Now, in some fields, this counts as scientific notation. In some fields, you have to put in the decimal point and the 0. It really depends on what your field is and what the expectations are. And notice here, again, I grouped the 10s together because I know 10 to the 5th over 10 to the negative 3rd is going to give me 10 to the 5th minus the negative 3rd when I bring this guy up on top. Woohoo. Kind of woohoo. Let's do the last one, and then we're done, and we can go to the Pokemon raid. Yay! Okay. And I'm not saying that the other sciences aren't fine sciences. I'm just saying they're not as pure and logical and perfect as math. Okay. 0 point. Oh my goodness. Let's see. 1, 2, 3, 4, 5, 6, 7, 8. This is the problem. 2, 3, 4, 6, 7, 8. With writing out decimals in standard notation. 1, 2, 3, 4, 5, 6, 7, 8, 9. Believe it's 9, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes. So this is 6.1 times 10 to the negative 9. That's the first number. Second number, 3,500,000,000 is going to be 6, 7, 8, 9, 3.5 times 10 to the 9th. Interesting that they worked out that way, almost if someone intended it that way. I totally did it. There's not even, it's not even a secret agenda. It's straight up, I'm going to tell you. I wrote it so it works out nicely to try to show you a little bit of beauty in the world, even though, you know, it can be an ugly world, but every now and again there are these beautiful flashes of synchronicity, especially if you plan them that way. So remember that when I'm multiplying things together, I've got the commutative property. Everything can move around and multiply wherever I want it to. So I'm going to multiply the 6.1 and the 3.5 together, and then the 10 to the negative 9 times 10 to the 9th. Okay, I need my handy dandy calculator here because not everything in the world is beautiful. Some things are decimals. Okay, so I get 21.35. And then what happens here with my tens? Well, if I've got two bases and two exponents, remember from the last section, what I'm going to do is add. So I'm going to 10 to the negative 9 plus 9, which is 21.35 times 10 to the 0. Okay, so that is 21.35 times, oops, sorry. There you go. Times 10 to the 0 times 1, which is 21.35, which I'm very quickly going to switch over into 2.135 times 10 to the first power, because I moved the decimal point one spot, because this is supposed to be written in scientific notation. Bam, we're done. Now we get to go to Pokemon Go raid. Ha ha, evil stepsisters. Yay! Yay! Okay, awesome. Back to math in the next section. Woohoo, more fun with exponents.